Okay, hello everybody, and I'd like to start the procedure. And today we have the PhD defense of Mr. Vahid Ramezankhani, and his supervisor is Professor Stanislav Fedotov. And let me introduce. And also, it was conducted under support of Professor Keith Stevenson. Unfortunately, he left Caltech recently. So let me introduce the jury members and me. I am Evgeny Antipov, professor from Lomonosov Moscow State University and Skolkovo Institute of Science and Technology. I got my PhD degree in inorganic chemistry in '86 and Doctor of Chemistry degree in '97. My main field of activity is synthesis of new materials for energy storage, metal-ion batteries, and fuel cell superconductors, ionic conductors, and also materials with effect of colossal magnetic resistance. I'm corresponding member of Russian Academy of Sciences and the member of Academia Europaea, European Academy of Sciences. My H index is 50 and citations is about 11,000. Also, jury member is Professor Alexander Karsunsky. He received his Doctor of Philosophy degree from Merton College, Oxford, and following undergraduate education in theoretical physics. He currently heads the hierarchically structured material group at Skoltech. He given plenaries at different international conferences on engineering and materials. He has developed numerous international links, including visiting professorships at University of Roma, Italy, NCKE in France, and National University of Singapore. His research interest concerns development and improved understanding of the integrity and reliability of engineered and natural structures and systems, from high-performance metallic alloys to polycrystalline ceramics to natural hard tissues such as human dentine and seashell nacre. His H index is 56 and citation about 14,000. With great pleasure, I introduce the external jury members, and the first one is Professor Radostina Stoyanova. She is a professor of solid-state chemistry in the Institute of General and Inorganic Chemistry at the Bulgarian Academy of Sciences. The research of Professor Stoyanova is directed towards the clarification of the fundamental principles of intercalation chemistry and the targeting of these principles to the creation of new classes of electrode materials for lithium, sodium, and hybrid metal-ion batteries. Your expertise covers the chemistry of energy storage materials with a focus on relations between synthesis methods, short long-range structure, and electrochemical properties of electrode materials for rechargeable ion batteries and supercapacitors, as well as thermoelectric oxides, solid-state ionics, and utilization of electron paramagnetic resonance spectroscopy for assessment of the local structure of materials. In recognition of her scientific achievements, Professor Stoyanova was awarded the prestigious National Prize Pythagoras for outstanding achievements in the field of natural sciences. Currently, she is a director of the Institute of General and Inorganic Chemistry at the Bulgarian Academy of Sciences. She supervised 8 PhD students and edited Chemical Engineering Journal. Her H index is 45, more than 200 publications with more than 7,000 citations. Next jury member is Professor Momo Safari. He is a professor at the Faculty of Engineering and Technology of Hasselt University, Belgium, and leads the group of electrochemical engineering at the Institute for Materials Research at Energy Wing. He earned his PhD degree in electrochemical engineering from Université de Picard Jules Verne, France, in 2012, working with the group of Charles Delacroix and Professor Jean-Marie Tarascon. Momo was a postdoctoral fellow in the group of Professor Linda Nazar and Professor Michael Fowler at the University of Waterloo, Canada, before joining Hasselt University in 2015. He is interested in the fundamental investigation of electrochemical systems to shed light on and quantity of the charge transfer reaction and charge transport phenomena in the electrodes and electrolytes, as well as the aging phenomena. His H index 23 and more than 50 publications with more than 3,000 citations. Next jury member is Dr. Smagul Karajanov. He graduated from Karakalpak State University, Uzbekistan in 1986. He received a PhD in physics and mathematics 93 and Doctor of Physics and Mathematics degree in 2001 and the Institute of Physics and Technology, Tashkent, Uzbekistan. The main fields of Dr. Karajanov research are chromogenic material and devices, solar cell materials and solar cell photocatalysis modeling by first principle calculations and device modeling. Currently, Dr. Smagul Karajanov is senior researcher at the Department for Solar Energy, Institute for Energy Technology, Kjeller, Norway. Also, he's leading research Institute of Solid State Physics at Riga, Latvia, present. He's an editorial board member, Elsevier Journal Materials Letters from 2023. And he's also adjunct professor at Vellore Institute of Technology, Vellore, India, from 2023 up to now. His H index 34, more than 200 publications with more than 4,000 citations. And now I'd like to introduce the supervisor. Currently, his scientific supervisor is Professor Stanislav Fedotov. He received his Master of Science and PhD degree in chemistry at Lomonosov Moscow State University. He has been working in the better material field since 2011, collaborating with MIT, KIT, Freiburg, University of Antwerp, etc. Professor Fedotov focuses on the design, synthesis, and analysis of new prospective materials for energy storage and conversion, including electrode materials and electrolytes for rechargeable metal-ion batteries. Currently, he is assistant professor at the Center for Energy Science and Technology, Skaltech, Russia, active reviewer in Nature Publishing Group, American Chemical Society, and Gevante Chemie, Elsevier journals, instructor in multiple Skaltech courses, interim director of the Material Science program at Skaltech, and also he is a coordinator of the Mendeleev Institute on Chemical Technology, Skaltech Bachelor Program. His H index 17, more than 30 publications, and more than 1,000 citations. Also, he received already more than 15 international awards. And now I'd like to introduce the candidate, Mr. Vahid Ramezankhani. He graduated from Kharazmi University in Tehran, Iran, where he specialized in solid state physics for his bachelor degree. He obtained a Master of Science in Science and Materials of Solar Energy with honors from the National University of Science and Technology, MISIS, at still and Deloitte's former institute in Moscow, Russia. During his master's studies, Vahid focused on optimizing perovskite solar cell for silicon perovskite tandem solar cell. Motivated by a desire to explore new avenues in the field of energy storage, he embarked on a research journey at Skaltech. At Skaltech, Vahid dedicated his efforts to characterizing and optimizing organic materials for potassium-ion batteries. Additionally, he has expertise in synthesizing inorganic materials. titanium and vanadium-based phosphate, polyanion electrode materials for potassium batteries. Throughout his PhD studies, Vahid contributed to two different projects. One was headed by Professor Stevenson, Russian Science Foundation project. Another one was headed by Professor Stanislav Fedotov, also from Russian Science Foundation. And he already has H index 5, more than 10 scientific papers with more than 130 citations. That's all. And now I'd like to ask Vahid to present his talk, his presentation, and it is limited up to 40 minutes. Please make a full screen. Okay, go.
Thank you very much, Professor Antipov, for your introduction. And I would appreciate all jury members, and especially Professor Thesis Stevenson, joined to my defense. This project, since we didn't have a laboratory for synthesizing organic materials, we made collaboration with Russian Academy of Science. I received some materials from there, and I start to characterize and optimize the electrochemical performance for storing potassium-ion. Unfortunately, today I have I'm coughing, so I do apologize you in advance if you hear some cough or something like this. But I should speak a bit slower. So this project was conducted under support of Professor Thesis Stevenson's grant, as you mentioned. International Energy Agency predicted that there will be a unprecedented growth in demand for lithium-ion battery, because if we look at the fourth main sections, people are using lithium ion. There will be till 2040 at least 112 times more demand, especially for electric vehicles. If the demand is going up, we have to take care of resources. Lithium resources abundance in Earth's crust is not so much in comparison to sodium and potassium. Even both reserves of sodium and potassium is more than lithium. Therefore, if the demand is going up, we have to take care about the cost. This is the cost of main precursor for taking lithium, which is more expensive than sodium and potassium. Although sodium is more abundant, potassium has some advantages. Of course, electrochemical. It has improved ion diffusion. It has lower redox potential. Of course, it has graphite, which is main anode for lithium battery technology. It's not storing so much. It is storing, but the discharge capacity is very low in the case of sodium. But it is storing potassium. For producing anode material in lab, we are using for lithium and sodium technology, we are using copper column collector. But for potassium, we can use aluminum, because at low voltage, it is not making alloy with potassium. And it has higher electrolyte conductivity because of weaker Lewis acid. Everything started from 2004 when Professor Ali Iftikhari he implemented crucian blue and potassium half cell. He patented his invention, and he patented his invention, and he published in Journal of Power Source. Unfortunately, for 2 years, all information about him is removed from internet. His Google Scholar profile is deleted. His ResearchGate profile is deleted. LinkedIn profile is deleted. While he is very talented scientist, at a young age, he collected H-index 44. After 11 years, in 2015, Professor he from Maryland Institute of Energy, he introduced organic potassium by using PTCDA. After this time, all compounds reported for potassium-ion battery technology up to 2022 is showing around 3,000 publications. From these 3,000 publications, more than 50 correspond to the organ. It means that 2% of publications correspond to organic materials. Because obtaining results from potassium is a bit challenging in the lab, and working on potassium extremely difficult project. There are a couple of global startups emerged from SNILS Group Fund. They claim that they will give the first practical device till 2027, and at least motor they will commercialize their pollution white products. I got this information from internet, so I'm not sure. And potassium-ion batteries market outlook, some market guys, they are telling it will reach to 4.1 billion in 2031. If we have some compounds published in the papers, because potassium has some similarity in ion storage with lithium, let's look at the electrode materials in lithium-ion battery technology. Firstly, here we have a plot. It is showing redox potential versus specific capacity. Lithium iron phosphate is well-studied materials up to now. It has a theoretical capacity around 169, with average potential around voltage around 3.4. Here, if we look at the benzoquinone has two functional groups. It has around theoretical capacity around 500 and voltage around 2.8 volt. So by calculating the theoretical energy density, lithium iron phosphate has 550 and benzoquinone has 1,400. So it means that for organic materials, this kind of high theoretical capacity is kind of offset to today bad voltage. Also, organic material, they are tunable. We can add more functional groups. For example, benzene, to tune the potential or to improve the specific capacity for some purpose. Or if we look at the lithium-ion technology, they have lithium inside the structure. We can in synthesizing process, we can introduce lithium inside the organic material and make organic lithium salts. In addition to, another advantage of organic material, they are not ion specific. Lithium iron phosphate may be used for just lithium technology, but these organic materials, they are usable for sodium and potassium-ion battery technology. Nowadays, if we develop further and work on polymer batteries, we may address the intention of the society in making thin film and small and thin, small and light flexible organic devices. This is a motivation that I work on novel organic electrode materials, not reported anywhere. It is made in Russia. We have two small molecules and 6 polymers. P1, for example, stands for polymer 1 to P6. P7 and P9, they are another group. There are some profound hypotheses in synthesizing this kind of material. Just the first thing, if you look at, they have first hypothesis is by introducing more functional groups, making them making them the candidate for high theoretical capacity. It is evident from here. There are other types of hypotheses. I would like to go in details in following slides, but I divided my work to 3 chapters. Chapter 1 to small molecules, chapter 2 these 6 molecules, the molecular structure, and chapter 3 molecular structure. They have different structure: planar, non-planar, conjugated, rigid, ladder type. So I'm going to open for you what is the purpose of designing this kind of method and what we are looking for. So if I should know better the existing material in the scientific publication, they are divided to 5 groups. The material I'm investigated located at the core. Some solar cell guys, some polymer guys, they are dividing based on their functional group. Some solar cell guys, they are dividing them based on N-type, P-type, and so on. So if we are going to make practical device, we should solve this problem. Problem correspond to carbon emitter. They are soluble. Because of solubility, they have a lot of problems. Capacity is fading. Although inorganic materials, majority of them, for example, LFP is not soluble. They have low conductivity. Low conductivity causing that some scientists, they use 40% carbon nanofiller inside the structure and 10% binder. So when we have this situation, absolutely the material is not doesn't have any application, 40% or 10%. Because lithium iron phosphate, people are using 90% wet person. As you can see here, the majority of organic materials they made from nitrogen. Excuse me, I changed something in my. Sorry for that. So challenge, they have low mass density. Lithium iron phosphate, LFP, it has iron inside the structure. This transition metal, the mass density for LFP is 3.6, but for organic materials, it is absolutely low. It is 1/3 of inorganic material. Therefore, we are using 50%. So when we are using 50%, we are not able to show application of material. they have, as I mentioned you, they have capacity fading. They have low Coulombic efficiency. William et al. Firstly, they introduced dichlorocyanuric acid as cathode in 1969. I should tell you, this problem stays from that time. My mission and task is to solve this problem. By 11 investigated material I showed. To solve my problem, I have to I have to develop some aim and objective. Aim is investigating carbon containing material in half cell. Please, it is not battery. It is half cell where potassium, I'm using potassium anode. Another thing, because I want to study my material. That's why I should use metallic potassium. The objective is, first, I should investigate the material based on molecular structure. If they are working, then I should optimize them. If I optimize them, I should show the mechanism. If I show the mechanism, I should improve capacity fading. I should solve Coulombic efficiency problem. I must optimize I must improve mass loading to be competitive with inorganic counterparts. I must maximize potassium energy density, power density. It is a lot of problems. Initial Coulombic efficiency. The basis of my research in the laboratory is coming to two objectives. Based on this strategy, I move forward. At the first thing, I must solve the specific capacity where we have 40% carbon nanofiller. We are keeping 40% carbon nanofiller to achieve the first objective. The first objective is telling to use new molecular structure, use new electrolyte formulation, and solve the capacity fading of the battery. The next objective, which is more important, is to maximize the gravimetric capacity. Gravimetric capacity is meaning that the most challenging part of my research is here. The most challenging part of my research. I should reduce the amount of carbon inside the structure. While some of the carbon containing materials, they have very bad conductivity. So the first part, I'm going to use 2 tetra-azapentasin based small molecule. The first material is OHTAP. It is tetra-azapentasin based material. It has high theoretical capacity by considering 12 functional groups. And theoretical capacity, we are using the number of electron transferring here at the end. So to move in the direction of the first objective, I have to use 40% super P and 10% PVDF. While I have KTFSI in dual DNA. The first hypothesis in using this small molecule is that the final conclusion from scientific papers telling that a structure should be planar. A structure should be planar to most likely reduce the solubility of the small molecule. Probably, we don't know. When I use it in the cyclic voltammetry, I saw broad oxidation. Battery scientists, they are telling, oh, okay, it is probably supercapacitor or pseudocapacitor. I should mention that we have potential change when one of these functional groups taking potassium, and this potential change impacting an entire small molecule and making broad oxidation rate. It means that we have 12 6, they are packed in one single bag. That time it was a breakthrough. I got the result from this material because there was a big attempt in Russian Academy of Science to get the result. That time it was for them it was a big breakthrough and came to our first publication. Unfortunately, they have very smooth charge and discharge profile. It is not similar to inorganic material. They are showing plateau. So we should, in following slides, I should explain everything detail by detail why this stuff is happening. After the first experiment, I came to early conclusion, and I come to some recommendation to collaborate. Conclusion is telling we should use new electrolyte formulation. It is my task to use new electrolyte formulation to solve this problem. Another thing is telling the second problem is originating from the molecular structure. Guys, believe that CH bond here, it is hindering ionic and electronic transportation inside the. So they came with the second hypothesis. They told if we introduce two functional groups here, if we introduce two more functional groups, we will increase the conjugation of the system. So OH-TPAQ, the hypothesis behind OH-TPAQ and the relation with it is planar conjugated to solve some kind of capacity fading of the battery to improve electronics. So I implement two strategy in my work to this planar and aromatic structure. So to move in the first target, to achieve the first objective, again I have to use 40% of carbon nanofilter. While my material has theoretical capacity around 85 to, I use intentionally. There are some reasons I use 100 millivolt per second, very fast scan rate. I want to show something why I use it. And the rate capability came to 21 ampere per gram. 21 ampere per gram, it means that it is discharging during 25 seconds. And cyclability improved from 50 cycles in the case of OHTAP to here I show you 1200, but actually it is 2700 cycles. It was gradually increasing and reaching to around 190 from around 100. So I use the linear part of the graph. So I'm showing here I'm showing here 1200. So according to I must investigate the metal line. It is showing.
I'm afraid we
it
went
is
a
storing
second.
them.
Could you
So
please get back?
get back. Yeah.
Vahid, maybe it's not the previous slide, but because it was a matter of 20, 30 seconds, most probably, not more. Thank you.
Yeah. 20, 25 seconds. So if the first objective is working, I should investigate the mechanism. Polymer guys, they are telling the mechanism is redox transition. transformation, transition. It is not, in inorganic chemistry, inorganic material, we have intercalation insertion. I should tell you it is some kind of insertion. So if I'm correct, why practical capacity is 190, but theoretical capacity is around 800, 1/4 of it. Because not all of them they are storing energy. When we are making 14 functional groups, just 6 ion storing. Because of a strict hindrance effect. A strict hindrance effect is hindering the reaction. So metal ions, they are falling in between, not any functional group they are storing metal ions. And regarding the functionality of pyrazine ring, XPS data, when I charge and discharge sample and use high resolution oxygen ones, nitrogen ones, reaching the carbon oxygen double bond to carbon oxygen single bond, and breaking the shifting carbon nitrogen double bond to carbon nitrogen single bond, confirm the hypothesis. And this is the SEM image of the pristine electrode, distribution of the macroporous, and of course huge porosity of the pristine material, which enabling this material for nice electrochemical reaction, as you saw there. And the impact of decline-based electrolyte didn't deteriorate active material after 2,700 cycles. So at the first objective, somehow I moved good. I want to tell you, in majority of scientific papers, people are claiming that metallic potassium anode has big problem. They are correct. They are absolutely right. Because surface of metallic potassium is very active. It is making KO2, which is very porous material. And this porous media is making solid electrolyte interface. In addition, from porous and non-continuous, from porous and continuously breaking SEI, we have dendrite grills, even at very low current, as low as 0.2 milliampere hour per square centimeter. Here is one example, OHTAPQ, that planar conjugated material that work perfect in decline-based electrolyte. When I use CAR-TFSI in dual DME, at the first cycles, if you look at here we have non-Faradic reaction. It is coming from SEI, falling down because of dissolution. This material is dissolving inside binary solvent, means dual DME. Then here it is the problem of metallic potassium is emerging, dendrite formation. The next thing, as I told you, scientists, they feel that this material is supercapacitor, pseudocapacitor, supercapacitor. If we want to address this question, we have to tell, okay, we have diagnostic approach to understand the potassium ion storage mechanism. As I tell you, I use this for very high scan rate. So I'm telling you, I didn't see problem with metallic potassium, although in a scientific paper, people, they are complaining of metallic potassium problem. The next thing, in cyclic voltammetry, current is product of summation of diffusion controlled process and capacitive controlled process. Diffusion controlled process is the same thing we see in LFP, lithium iron phosphate. In other words, we can tell this formulation as A scan rate in power of B. The B value here has a specific meaning. If the B value is 0.5, it means that diffusion controlled behavior we have. If the B value is falling between 0.5 and 1, we are in transitional area. We have some kind of capacitive contribution, right? And I got B value by mathematical tools, by taking the slope of curve. So we have both process, diffusion controlled process and capacitive process. So all things mentioned here about the achievement of first experiment for small molecules regarding the regarding the cyclability, regarding the electrolyte formulation, and other things. But for second objective, I failed. When I reduced the amount of carbon nanofiller from 40 to 20%, gravimetric capacity didn't improve. Why? Because of supermolecular packing effect. Why we have supermolecular packing effect? Because we are introducing 14 functional groups in this structure, and we are improving the steric hindrance effect. So what should we do? Probably polymerization, by making it planar polymerization, by making it non-planar. It means that we distribute functional groups in non-planar structure. Why we should put all the functional group in one structure? And another thing, the impact of pyrazine ring, which is embedded in the structure, should be further identified. Is it better we have embedded pyrazine ring inside the structure, or it is better we make some kind of imine bond? It means that we make exocyclic carbon nitrogen double bond. Based on this hypothesis and recommendation for discussion with my discussion with our collaborator, 6 triquinol polymers, triquinol derivative polymers introduced. Sorry. 6 polymers, they have, so as I promised you, now it is the time to go into detail to show what is the hypothesis behind the designing these molecules and how can I match them together. The first material is planar. Why it is planar? Polymer scientists telling, if we have planar units and we make them polymer, for example, unit 1 here, unit 2 here, unit 3 here, we can make robust structure. Probably this planar structure will not dissolve inside the electrolyte, and we can improve the gravimetric capacity. Probably. Let's see. Polymer P2 has some similarity to polymer P1. Polymer P1, we have symmetric benzopyrazine here, right? But polymer P2 is planar, but we break this symmetric structure. By breaking the symmetric structure, we maintain conjugation and we made it rigid structure. What is the ideology behind making polymer P3, which is completely different from others? In previous experiment, I showed you redox potential is around 1.6. Guys, they thought if we introduce 2 bridge of anthraquinone inside the structure, we may improve the redox potential, because anthraquinone itself has 2.3 volt redox potential. So we must see, does this hypothesis working or not? Another hypothesis, they made it non-planar to distribute functional groups in different parts. The same hypothesis for distribution of functional groups appear in P4 to P6. P4, we have phenylethylamine bridge here. It is giving 50% planarity, 50% non-planarity. Why? Because this ring stay on the plane, and we have rotation 90% for this non-planar structure. Then they started to add two bits here to produce some kind of non-homogeneous functional group. And here they made 3 phenylethylamine rings, phenylethylamine beads, to make distribution of these functional groups, nitrogen functional groups, homogeneous, right? So what can I tell you? If I tell you the difference in whole materials, I can tell you we have benzopyrazine embedded inside the structure in the case of P1 and P2. However, we break benzopyrazine and make exocyclic quinoxalin. Please have a look at here, CN. It is exocyclic. It is not embedded inside the structure. So we are going to see and compare the performance. A leader material, polymer P1. I label them based on a specific capacity in the direction of objective number 1. As you can see here, super P is 40%. Again, we see the same signature for cyclic voltage model. But here we have polymer. So in addition to electronic impact of functional groups on each other, when we have polymer, we have polydispersity effect. It means that the length of chain in polymer is different. This is another reason in polymer we have some kind of single bond. Please do not expect if we have 20 functional group, we should see 20 peaks. No, we don't have the same situation. It has good rate performance. It is showing 12 ampere per gram, which battery discharge, I think, around 45 seconds. Half cell, 45 seconds. Again, I use linear part of the graph. And unfortunately, average potential is around 1.6. Do not make presentation very boring. I make a table here. I should answer this question. First, the hypothesis I told you. They want to make high theoretical capacity. Why some materials with planar, non-planar, they have different cyclicity? I should answer this question when I'm matching the electrochemical performance to molecular structure. And my first objective is working up to now. If you look at the final capacity, is higher than initial capacity. And I should answer another question. Why redox potential for different polymers is different? And I should mention that this is a specific energy density if we consider 40% carbon nanofiller and 10% practical specific capacities, half of it. Absolutely half of it. Then, to answer the first question, why capacity of the P1 is high? Because of the symmetric distribution of benzopyrazine, right? And another thing, when we are going to rigid a structure and we are breaking this symmetric structure and making the structure rigid, the practical capacity is reducing to 40%. And when at polymer 3, when we would like to distribute the functional groups in non-planar structure, and of course improve the redox potential by adding two anthraquinone bridge, we are making our material more soluble with very bad cyclability. However, the P4 situation, because it has 50% planar structure, far better than P5 and P6. Why? Because it is 50% planar structure. P5, because of non-homogeneous distribution of functional group, and of course adding two phenylydiamine bridge, we made it soluble, and its cyclability is around 150. However, for P6, because of distribution of homogeneous distribution of functional group, we have 1000 cycles. To answer another question, why the average redox potential is different? If you look at the semiconductor physics, we have for solids, we have conduction band and valence band. But in polymers, we have LOMO and HOMO. When you are introducing electron donating groups here, they are electron donating here, they are donating electrons. Donation of electrons means HOMO energy level is coming up and redox potential is coming down, as you can see in the case of P3. But in the case of P2, because of less amount of electron donating groups and rigid structure, we have P2 around 1.84 volts. And for P6 and P5 as well, more functional groups leads to less redox potential. Why for P5 is less? Because oxygen is more electron donating than nitrogen. So objective 1 is achieved up to now for all materials. But objective 2 again is failing. Objective 2 is telling first move to 20% of carbon nanofiller. While when I did 20% of carbon nanofiller, none of these materials work, none of them. Then I make electrode thicker. Some polymer guys, they are telling for polymers, because of their low mass density, when we are reaching to 1 milligram per centimeter square for thicker electrode, it is big achievement. So I make thicker. The conclusion is P2 is showing better gravimetric energy density. Why? First, because it is rigid. The next is it has smaller particles, greater surface area, 27.2 square meter per gram. But for other materials, non-planar fail. So it is better we stick to the planar structure, conjugated planar rigid. The third conclusion I'm telling you here, making a lot of functional group, introducing a lot of functional group in the structure is very bad. it is better to not make complex molecular structure. It is better to make them as simple as possible with homogeneous distribution. The next thing, if we investigated pyrazine ring inside the structure, so what about other rings? We have other rings. It's better to investigate other rings as well. The final thing, my recommendation, it is better to move to ladder structure, not planar or non-planar. Planar and non-planar is good, but let's investigate ladder structure. So the chapter 5, the idea for
Vahid, you spoke already more than 40 minutes.
I'm Professor, a bit. I have I have
already.
a call to do.
Please.
Yeah, sorry.
Yeah.
Sorry, I'm moving
maximum
faster.
3 minutes.
Yeah. So therefore, we introduce pyro. Excuse me, Professor. I'm ill today, so I have to. I cannot speak faster. If I speak faster, I will cough. So, introducing synergic usage of pyrothiophene and dioxin group with using pyrazine ring shed some light here. When we are using 50% of 50%, so they have again good cyclability. But when we are reducing the 40% to 10% multi-walled carbon nanotube, we are pyrazine ring is working very bad. But for pyrothiophene and for dioxin group, it is working better because of electronic conductivity. My next objective is to improve initial Coulombic efficiency. Therefore, I add current. I increase the current density, and I saw that this morphology of this pyrothiophene containing material is giving 83% initial Coulombic efficiency, which is very important with nice morphology. But when we are making grainless and we are nanosizing our material, we are reducing the initial Coulombic efficiency to 52%. So the second objective for P7 already, for P7 and P8 already achieved. So I want to tell you a structural electrochemical property of my material. A structure, they are planar and conjugated. So if a structure planar and conjugated, they have high capacity and cyclability. In the case of these polymers, a strict hindrance is increasing because of so if the strict hindrance in the case of this non-planar structure is improving, we have less practical capacity. And when we have rigid and ladder type structure, we can optimize our mass loading. So not only the problem solved, based on redox potential, I divided my material, my graph to the 4-port. The material is showing better performance at the identical condition in the half cell for P1. It's kind of a record based on my knowledge, and for P8, it is showing good anodic behavior based on redox potential, and based on energy density and power density, we have for P1 comparable result with one of the best recorded result, DPPZ, which I'm corresponding in this paper as well. And the objective number 2 here, by increasing active mass content to 85%, which is far better than other reported result already. So to put everything in nutshell summary, a small molecule, it showed 41,000 watt per kilogram. We have 6 polymers. They have leader polymer is showing 422 milliampere hour per gram, which is helped me to achieve the first objective, not only, but also highest amount of specific capacity reported so far. And ladder type benzoquinone material, they are showing improved gravimetric capacity, as you saw there, with improved initial Coulombic efficiency to 83%. This is the result of 4 publication. I would like to thank my supervisors, Professor Stevenson, Professor Fedotov, and my dear jury members who join and spend their time to comment in my dissertation. My colleagues from Russian Academy of Science, Schooltech officials permitted me to be defense be online, and PhD department colleagues, Elena and Nadiajda, and my family and friends, especially Sergei Marshenia, who printed my dissertation. And thanks for your kind attention. I hope my coughing doesn't please do not take care of my coughing. You ask as many questions as you like. Thank you very much.
Thank you very much, Vahid. And now we are going to the next questions and answer session. And I will ask each member of the jury to ask any questions. And what is important also that he or she should say whether is satisfied or not with the changes introduced to the thesis after the review. And firstly, I'd like to ask Professor Karsunsky to ask questions and also to state either he is satisfied or not with changes. Alexander, please.
Yes, I'm just switching on my camera and microphone. Hope you can hear me. Vahid, you have presented a rather interesting, thoughtful rumination over what you've tried to do and what you've managed to achieve, verify as hypothesis or falsify. I'd like to ask you perhaps a somewhat philosophical question, but nevertheless an important one. Is it worth it? So what is your assessment of the perspective, the likelihood of the development for successful potassium-ion organic batteries?
Dr. Kortunsky, thank you very much for your question. As an experimentalist who worked 6 years in the laboratory, day to night, even vacations, holidays, I'm telling you, I'm very optimistic to make full all organic batteries. Since I have broad view, I work on inorganic materials and organic materials. Of course, these findings is very important. If I continue my work, for sure, I do promise you I can do this job by some changes I should apply to the material. First, we need further molecular structure change to make them more competitive to potassium.
Competitive is not a very scientific term. It may be an engineering term, but I'd like to know what you mean by competitive and with what? With other inorganic systems for potassium ions, with other batteries, etc. Just please get the point that I'm trying to make. What you've shown suggests that the working voltage, the capacity, etc., is not quite reaching the levels that are sought by today's new technologies. So how are you going to reconcile this with making this the result of this research competitive?
So thank you very much, Professor. I want to answer your question in detail.
Yeah, please.
Yeah, Professor, if you look at here to my research methodology, here you see an arrow here, right?
Mm-hmm.
So it means that I have some objective, right? The material I investigated, especially polymer P7, I think it has some kind of, it is anodic behavior. It can be competitive with current lithium-ion battery technology. Why? I had for my research methodology. I had some talk with guys in industry, and I continued this work in the lab. It was very difficult project. They told me graphite is problematic material. Technology of making artificial graphite under control of China. If you can introduce new polymer material that serve as an anode in lithium iron phosphide technology, you will be able to make some kind of predictor. Based on this, I made this. So I implemented my idea in the lithium ion technology. If lithium ion technology works, I will move further. You know what does it mean? 6.3 milligram per centimeter mass loading of the polymers, while they have density around 1.8 milligram per cubic centimeter. Layer will crack, but I use 90% of mass loading, very thick electrode, and the ideology worked. And when I made when I implemented full cell, the ideology to implement polymer inside lithium-ion battery technology is working already. So the thing I need to do, I need to optimize system by doing some changes to molecular structure of material to make them to introduce practical application of my method. So this is I think my answer is somehow clear.
Okay. The next explanation that I would like to ask for is this. You talk a lot about molecular structure of the polymer part of your system. The fact that you can use diffraction to study the crystalline part is clear, but you were talking about steric hindrance effects and planarity, etc. What experimental methods, perhaps it requires reiteration, did you use to ascertain this aspect of the
Thank you very
structure?
much for your good question. We experimentalists, we have some ways to understand our polymers as crystal structure or not. When some organic electrochemist in the lab is doing cyclic voltammetry, and especially DQ-DB technique, if the distance between oxidation and reduction is more than 1 millivolt, here we can think that we have crystalline structure, especially when we have rigid structure. I tested in XRD. They are absolutely amorphous. But if we make organic potassium salt, as I saw in reports, they will have crystal structure. So I included the XRD data. Professor Antipov asked this question. I included in the logo change. So none of these material they have crystal structure. None of them.
If you study them not using XRD but by differential scanning calorimetry, do you have peaks corresponding to crystallization?
No. Absolutely amorphous.
Okay.
I didn't see any peak. It is
All right.
showing broke because of using a lot of functional group inside the structure. If we make rigid structure with homogeneous, and of course we make lithium, we make organic potassium salt, I guarantee you we will see crystal structure.
Okay.
As I see in the scientific papers.
Yeah. Okay. Thanks very much, Vahid, for answering my questions. Dear Chairman, I'm satisfied, and I am happy to recommend this candidate's work for the award.
Thank you, Alexander.
For your nice
and now I'd like Professor Radostina Stoyanova to ask any questions to the candidate and also to state either you are satisfied or not with the changes introduced to the thesis after the review. Please, Radostina.
Thank you very much, Professor Antipov. I'm happy from the presentation of Vahid. I have some previous question, and now some additional question arises. One of them is, I wonder why the capacity of materials increase during the cycling. This question is related with the first, my previous question. If the capacity increase during the cycling, this means that some additional electrochemical reaction occurs. Vahid, could you give some comment on this effect?
Thank you very much, Professor, for your question. I can answer your question from three or four, yeah, I think three aspects. The first aspect, why capacity is increasing. The first aspect, you should look at the molecular structure. If you look at here, we have many functional groups. When they are working, they are one by one getting active. At 50 cycles, 2 functional groups. 100, 3 functional groups. 400, majority of them, 5 of them. So this answer based on molecular structure. The next thing is because of the experimental work in the lab. When we are making electrode, crystalline electrode with this quality, we should expect the raising of the capacity because of the macroporous distribution and of course huge porosity and surface area of the material. The next thing, I should answer this question from third aspect, electrolyte. Lignin-based electrolyte, it has a chelation effect. It is making metal complexes. Lignin-based electrolyte, it is making a stable SEI, especially when we are using 2.2 molar. Lignin-based electrolyte doesn't have problem with anodic metallic potassium. And the final thing, you correctly mentioned that probably some capacitive behavior emerging here, but to reduce the impact of other factors, as you told, I put voltage here 0.7 volt to 4 volt. So I didn't go down in the voltage because why? Because carbon contribution in the capacity will raise if I reduce the cathodic potential to down. So I kept it as 0.7. Therefore, contribution of carbon in the capacity as I calculated is around 25 milliampere per gram at this current density, 25. But if I go to down, for example, 0 volt, we will see now SCI contribution or non-Faradic contribution in the capacity. We will see contribution of carbon, which is around 100 milliampere per gram. So I control these things. So that's why the capacity is raising.
Okay, but if you come back to previous slide, the curve mimics the supercapacitor behavior for the carbon materials, it is well known that capacitive behavior is well known for the carbon materials. For this picture, CV curve, here have some peaks, but I think that in this case, maybe the mixture between Faradaic and capacitive reaction take parts. And in this case, my question is, it is possible to quantify the ratio of the capacitive and the Faradaic reaction? And what is the role of carbon additive in order to improve the capacity, maybe due to the capacitive reaction?
Yeah, thank you very much for your question. Professor, as I showed you here for a small molecule, I told you we have it is not supercapacitor, it is pseudocapacitor. We have, I confirm your statement that we have capacitive contribution here. And even in my
Excuse me for a moment, please. Could you explain how to determine the current in this CV curve?
How to determine the current? So
Yes.
I use the highest current, and I plotted them here.
Mm-hmm. Okay.
Do you hear me?
Okay.
Yeah, I took peaks here, and I calculated them here. But in the case of P1, polymer P1, I should tell you in dissertation I included that because Journal of Material Chemistry reviewer, they asked me, and the B value is 0.77. Yeah, we have capacitive contribution. I 100% agree, but it is pseudo capacity. So how to determine it?
Yes, for example, it is possible to quantify the mixture between Faradaic and capacitive reaction using the difference scan rate, and it is possible to relate the capacitive reaction with the content of carbon that you are using in order to prepare the electrode, because the electron conductivity of organic compounds are relatively low.
Yeah,
But
Professor,
of
it is very good
course,
comment. Yeah, it is
please.
very good.
Yes, but of course, this is another direction of the investigation. In general,
Yeah.
I'm satisfied, and I think that you have do a great work concerning potassium ion cell, which are at how to say yearly maturity. For that reason, I give you the highest mark for the presentation and the defense of your PhD thesis.
Thank you very much for your kind comment.
Thank you very much,
appreciate
Professor
Thank
Stoyanova. Are you satisfied or not with the changes introduced?
Yes, I satisfy.
Thank you very much. Thanks. And now I'd like Professor Momo Safari to ask any questions and also to state either you are satisfied or not with the changes. Please.
Hello, thank you, Vahid, for your presentation. I like it because it was presented in a very confident way, and I like it. So it shows that you work on your topic with the with passion. So, and that's something that's very appreciated. First of all, I'm happy with the also changes that was made to your thesis. So so I don't have any comments over there, but indeed I need to follow up on the questions that my colleagues did and ask you a few questions. So the first maybe question I would like to address is one of the main motivations you use at the beginning of the presentation was sustainability of potassium batteries compared to the other type of batteries. So, and that was clear. But in terms of making your electrodes, if I remember correctly, you use a NMP-based, let's say, a slurry formulation to make your coating and electrodes. Can you comment on your, let's say, perspective on making aqueous-based, let's say, processing? But I'm sure that there are some reasons. Maybe it's related to solubility and this kind of thing. But what is your general, let's say, reflection on that aspect of making electrodes?
Yeah, thank you very much for your question. Yeah, if we make aqueous, we should use CMC plus deionized water inside the structure. So, unfortunately, the attempts for making it at the beginning failed because of cracking the layer, because of the non-homogeneous distribution of the slurry on the current collector. Then I came to the conclusion that NMP is better. Please note that if we have, imagine we have two NMP box. One of them we are keeping outside glove box, and another NMP bottle we are keeping inside the glove box, right? If we use NMP which is stored outside the glove box, because of a reaction with moisture, organic material, for sure they will crack. Electrode for sure would crack. But if we use NMP, which is we kept very isolated inside glove box, for sure the quality of our electrode is far better than aqueous type of slurry.
Okay, Steve, I see. Good, thanks. Maybe I can elaborate further on making the type of the electrode making process, and I don't remember exactly, but what is the range of thickness, the dry thickness of electrodes that you make? Because the porosity and dry thickness of the electrodes that you make after drying, let's say.
Thank you very much for your question. Because of so it depends. If I want to make improve the specific capacity, right? If I want to improve the specific capacity to achieve the objective number one micrometer, because the density of polymers I investigated is between 1.5 gram per cubic centimeter to 1.8. If I'm going to improve the if I'm going to improve the gravimetric capacity, the maximum 6 micrometer, as far as I remember.
Okay, I see. Good. And then maybe I can continue on that, and it also a little bit follows on the previous questions regarding the capacitive behavior of your electrodes. And as, again, if I'm not mistaken, the range of C rate. So usually you report the load of cycling in ampere per gram, not in C rate. But I remember that you mentioned, and also considering the specific capacities, you are using rather very high C rate. Yeah, I think easily above 10 C or something, if I'm not mistaken. And so then that raised this question that then these materials also could be very good candidates for supercapacitors, or let's say for power applications. And I don't see any problem with that, because that's performing, delivering such a high energy at such a high power. So that there is also a huge market for that. So can you comment on that? Because this I don't see much low C rate, let's say, performance, and that might influence the target applications. Because in electric vehicles, for instance, you are used to use an average C rate which is below 1 C. I mean, during the lifetime. So how you can comment on the application of your material?
Thank you very much for your question. I must tell you that I'm working on potassium-ion battery. So the first thing I should mention you is about potassium itself. You mentioned correctly why you are using high ampere current density, or for example here 21 means if we calculate based on 6 electron passing, it is 55 C, right? 55 C. So why I'm using this high current? So because it is potassium half cell. Potassium half cell, there are some kind of dendrite forming there, correct? There is a phenomenon in chemistry called Joule heating. For potassium ion, but because at low current density around 0.2 milliampere per centimeter, dendrite is forming. So potassium should, for potassium cell, we should charge it as fast as possible. Because of Joule heating effect, dendrite will be get softened. Why? Because the melting point of potassium is 63 degrees Celsius, while for lithium is 180. So this is the perspective of using high current. That's the first question. The second question, you mentioned correctly. You mentioned that which material is proper for supercapacitor. I recommend this material, P8, with the surface area around 238 square meter per gram. Why this material is better for battery application? So I think I hope it is convincing for you. Or do I need to?
Good. Of course, I acknowledge that I mean, this is kind of these materials compared to lithium-ion batteries are at an infancy stage. So I'm sure it's a lots of follow-up work and project you can make it better, and also your peers in the community. So I can finish, and so I can once again thank you for the good presentation, good piece of work, and lots of I think contribution to this challenging topic. And as I mentioned earlier, I'm satisfied with the modification. So I'm happy with you to be granted, let's say.
Thank you very much, Professor. I appreciate your nice comments, and I learned many things from your comments.
You're welcome.
Highly appreciate it.
Are you satisfied or not with the changes?
Yes, certainly I'm satisfied. Yeah.
Thank you very much.
You're welcome.
And for now, I'd like to ask Dr. Smagul Karajanov to ask questions and also to state about the changes, please.
So thank you, Vahid, for a very nice presentation. So I have 3 questions. One of them is it's related to how the material is safe to work with. Can you comment? Of course, this is new material, and maybe not much work was done. I don't know. So can you please comment maybe status of the problem?
Sorry, Professor, could you please repeat your question? I didn't catch what did you tell.
Okay, yes. So the question is how the material is safe to use, and it's toxicity, and can you comment on recyclability of this material?
Yeah, Thank you very much, Professor, for your question. This polymer is it's called green technology. It means that they are environmental friendly material.
Okay.
So we will not see so much challenges with polymers.
Okay. Good. The other my question is you have presented the performance of your materials, and what is the reference material to compare these references with? So this question is somehow is correlated with the question by Alexander Kharsunsky. So which reference material did you use for comparison?
Yeah, which reference material? So reference material, all these matter. For example, if I consider my electrode for cathode, this material here
Okay.
mentioned here, they are the best reported results up to now.
Okay. Okay.
Yeah. So with this identical testing condition.
Okay. Yes. So then the last my question is, have you tested the concept of pairing of P7 with high potential inorganic materials, possibly in lithium fuel cells?
Yeah, thank you. Thank you very much. It is very nice question. Professor, if we are material P7, if you look at here, material P7, it doesn't have potassium metal inside the structure, right? So if I use this material as the anode, and I come here.
Yeah.
It is a kind of cathode material which developed by one guys from Professor Stevenson's group developed it, and I'm co-author in this paper. This is cathode material.
Okay.
It doesn't have potassium inside the structure. If I make full organic battery will not work for sure. It will show open circuit voltage around 0. So I have to introduce metallic potassium inside the structure here. Here.
Okay.
Making it OK. If I make it, yeah, it is possible to show practical application, or plus some other type of modification.
Okay. Yes. Thank you. I'm satisfied with the changes, with quality of the presentation, and I recommend Vahid to the degree of PhD. So thank you for attention.
Thank you very much, Dr. Karajanov. And the last member is me, so I will be very short. And can you show the slide number 14?
14. Yeah.
Yeah, here. Actually, please explain me where the protons are going. First reaction at the top of the picture. So you oxidize.
Yeah, right.
And the proton are released. And where after that process, that protons?
It is some kind of hypothesis, and I can consult this thing with the polymer scientists, and of course I'm not satisfied with the explanation. So they told for oxidation we should consider this middle structure, but somehow I was not agree with them, and they told to somehow if we want to make if we want to show the reduction, we have to make first carbon oxygen double bond. But anyway, it is some kind of extra level of oxidation, which even it was not convincing for me.
So, as I understand, the protons, they stay in the system.
Yeah.
But
To show the mechanism, they
no, I
claim that.
understand the mechanism. I understand this is first and the second you showed. But I'm just asking that at the first stage, you oxidized and the protons are released.
Yeah,
If the protons
Professor,
are inside of the system, the battery will not work.
Professor, I understood what do you mean. Professor, do you know there is one step here. It is making oxygen radical. Which is a state that making carbon-oxygen radical, it is not stable. And polymer guys, they are not showing in the reaction. But honestly speaking, I saw in some publication, these at the first stage, here we are there are multiple stages, and we are making radical. Oxygen is turning into radicals. So because the formation of the radicals is not stable, it is not shown here, and we are ignoring. So it means that eight stage stay here. First, this oxygen is making radical, then this oxygen is turning into radical. I mean O dot. This OH is turning into radical O dot. After 8 stage.
Okay, I'm satisfied. Can you show me the table with the capacities somewhere at the end? Like here. So, okay, theoretical capacity. How did you calculate theoretical capacity?
Yeah, thank you very much for your question. Theoretical capacity is calculated based on this formula.
No, I know that formula. I know that formula, but I'd like to ask you. So you developed cathode materials.
Mm-hmm.
So it means for potassium-ion batteries, it means that you did not take into account potassium. In real battery, if you consider really the perspectives of potassium-ion batteries, these materials should be pre-potassiated. You mentioned in the text of your thesis, yeah?
Yeah.
But if you pre-potassiate it, that's another molecular weight. And what is the capacity?
So for sure, when it is pre-potassiated, for sure the capacity will come down. I mean, I calculated and I included in the published papers, we thought pre-potassiation stage. So yeah, you are absolutely right. When, Professor, here we have for example, here we have 14 functional groups, right? If we calculate based on that formula, it will show the capacity around more than 800, correct? So, but actually, based on DFT calculation, just six potassium is transferring. It means that the capacity is not 800. The capacity is 365 milliampere per gram. You are pointing very good. You are putting very nice comment. I appreciate it. Yeah, absolutely right. But in the text of inside the text of dissertation and papers, I mentioned.
And my last question, I'd like to continue what Alexander asked you. It's more philosophical. Momo Safari, he worked within the group of Jean-Marie Tarascon. And some time ago, Tarascon came to St. Petersburg and he asked the question about similar materials that from his point of view, that type of materials are useless because you need to make pre-potassiation. How you will answer?
Absolutely correct.
Yeah. Why
Yeah,
do
absolutely.
you believe in perspectives?
Absolutely, I believe.
Jean-Marie does not believe.
I absolutely. They should pre-potassiate it. Without pre-potassiation, they will not have any. They will not have any application. Firstly, by potassiation, we can improve the tap mass energy density. By potassiation, we can improve the we can make a practical device. However, my work was engineering. What can I do? Some synthetic guy, they can go to lab and make organic potassium salt. What can I do in the lab? I can go and take my material and dissolve in the potassium naphthalide, because potassium naphthalide is very, very reactive material, and make some kind of pre-potassiation. But absolutely, it doesn't have any application. And another thing, as I told you, these materials, they are dissolving inside the electrolyte. For making, when I make potassium naphthalide, I should use DME. So I will dissolve the material. So how can I do it? Your point is absolutely correct.
Okay, Vahid, thank you very much, and thanks for your nice presentation. And also, I'd like to state that I'm satisfied with the changes made in the thesis after my review. So now I'd like to ask questions from audience in Zoom. Yelena, anybody?
No,
there is no. Okay.
I do not see any questions.
Okay,
I don't see many members.
we go to the next point, and I'd like to ask the supervisor to say a few words. Professor Fedotov, please. Also, just a minute. I noticed there is Keith Stevenson, in Zoom. Keith, if you want, you can say a few words, after Stas,
Okay. All right. Dear Professor Antipov, thank you very much for presenting the award. So, dear Vahid, dear committee, dear all, so it's a pleasure for me to say some words in favor of Vahid. So, first of all, I'd like to start with saying that I'm really grateful to Vahid, so that I had the chance to work together with him, probably not directly as supervisor, but as a close colleague. So, and actually, I've been watching Vahid for more than 6 years, starting from the time when he came to Caltech as a master student. And after his successful graduation, he then enrolled in a postdoctoral, postgraduate program at Caltech and continued his research. So, totally, it appears that he has been working for a long time with organic electrode materials under supervision of Professor Keith Stevenson, but unfortunately a year ago Keith had to leave Caltech and I had to in turn take the supervision over Vahid, so since that time. And actually by that time Vahid managed to progress further significantly in the field of organic electrode materials.
Recording stopped.
For potassium-ion batteries, of course, so we at that point decided not to drop this research line, and we decided to finalize some of the work that was previously initiated earlier. So, and at the same time, we launched some new research on inorganic materials for potassium-ion batteries as well. And in this field, Vahid also achieved some tangible results and prepared 2 drafts of papers, which are still, I would say, under construction. So we haven't managed to include this data in this PhD thesis, but I'm sure this work will be published later. So let me also say some words about Vahid as a person. So as a person, Vahid is diligent, helpful to others, and really responsible person. So he is a really good team member. So and he is really clever. So he easily grasped and mastered new methods, including methods of synthesis, non-trivial methods of synthesis, and non-trivial chemical tasks were fulfilled by him easily. So I hope really that we will publish some data soon, and because Vahid contributed significantly to our research in the group, and also I think he's really ready and mature to be a PhD awarded person. So from my side, I also wish Vahid luck and success in his future endeavors, and hope we could meet someday in person. So I'm done.
Thank you very much, Professor Fedotov. And now I'd like Professor Stevenson to say a few words. Keith, please.
Thank you, Evgeny. Well, first of all, thanks to the jury members who did all the due diligence to read through a massive amount of experiments. And of course, there were some typos and other things that over the course of this process he significantly improved, including this presentation here. And I just want to see this points to Vahid's persistence, not only as a scientist to really improve his work and understand his work, but just how he doesn't ever really quit in terms of his passion for actually doing really good science. And you know, he came to Russia with the hope of getting a PhD, and first he started at Mises working on perovskite solar cells, and then became a master's student at Skoltech in the very beginnings of our program. And this is where I had this project that was funded by RSF on looking at organic materials that could be suitable for not only lithium, but beyond lithium. And so over the course of these studies, we learned really a lot with regards to how to benchmark these materials, how to quantify the materials, how to study, in particular, the influence of the electrolyte and the solubility. And now we see that we contributed to a lot of new knowledge in the area of potassium-ion. At the time, no one was really working on this, as he highlighted in his literature citations. And now this is all in vogue. Everyone wants to be making sodium and potassium type batteries. There's a few startup companies now really trying to make a go of this. And yet they have to now refer to Vahid and some of my other previous students' literature publications to actually understand if this will really work as a commercial technology. And the case in point is, yes, it would be best if you could pre-sodiate or pre-potassiate these materials. As we know, John Goodenough made lithiated cobalt oxide, and this allows you to assemble the cell in a discharged state, thereby being safe to then charge the device and then with a suitable anode material make a rechargeable system. So there still is a long ways to go with realizing potassium-ion batteries, but I think still being in the forefront of the scientific envelope of this, we could maybe really see the full realization in maybe 10 years or so. And of course, the applications will not be for transportation, but maybe suitable for other types of energy storage concepts, maybe grid scale, including other limited hybrid type utilizations, for instance, conformal batteries that make up the skin of some type of physical structure, functional structure. So again, I want to thank Vahid for really for being persistent and diligent in his studies, and to really cover a very large phase space. The difficulty in general with the materials he showed is that in general they're all amorphous, and so therefore there's very little spectroscopic studies that can be done to help elucidate the mechanism. And you see that simple organic chemists like to push electrons to show reversible redox transformations, but yet we still do not know fully the full mechanism of what's redox-active and how the redox potential shifts with regards to substitutions within the backbone or making it more rigid. Yet this library of compounds does serve as a basis for future understanding. So Vahid, congratulations to you and to all your persistent efforts to realize your thesis, and I look forward to interacting with you in the future as you become a successful potassium-ion battery scientist.
Thank you very much, Keith. Now we have a closed session, and I'd like to ask Elena to organize, because we have to discuss, to vote.
Yeah, sure. So right now I will open a breakout room only for the jury members. We will ask Professor Fedotov to leave the classroom. Vahid, Professor Stevenson, and other audience online, if any.
Okay. For Vahid, after discussion with jury members and voting, the final result is the following, that all jury members voted that your thesis is accepted as is, and even more, some of them, they stated high quality work which was done in your PhD thesis. So, and now I'd like, as a chair, to congratulate you with really very good PhD defense, and wish you to continue to work in science efficient as you did before, and to produce much more exciting new results. So congratulations, Vahid.
Yeah, thank you very much, Professor Antipov. Firstly, I appreciate Professor Stevenson and Stanislav Fedotov for all the support they did during this time. They consult me, and highly appreciate the jury member who put valuable comment in my dissertation. Even they ask good questions. I learned from you, actually. I hope my life condition allows me I stay in science, because I'm sure I can do something. I can make a visible device. And I would like to keep my connection with all jury members in future. If I see I need some help, I ask them questions, and I ask them to advise me, and finally I compensate they good comments and questions by having a joint publication with them. So thank you very much again. Thanks a lot for your time, for your support, for your help.
Okay.
Congratulations.
Okay. Yeah, congratulations to you, both supervisors, Keith, Professor Stevenson and Professor Fedotov, for the great defense which you did today, and thanks all jury members for participation. And now I have to close our meeting. Vahid, good luck.
Congratulations, and good luck.